Do we have a go? Did we start? Alright, welcome everybody to our DataWorks meetup. We do this every 2 months and we try to discuss topics that are interesting for both data engineers and data scientists. Today we have an experiment because it's about languages. When you put languages to engineers, you can always get heated discussions. So I'm very curious where we are ending up with. We have a discussion between a data scientist and a data engineer. We'll see whether it's a heated discussion or whether we can learn from each other, because that's what we're actually trying to do. So welcome everybody, and I want to welcome Thijs and Tim, and have fun with this talk. If you have any questions, please put them into the chat and we will ask them to the presenters. There is a slight delay forced on us by YouTube, so don't be nervous if the answer will be a little bit later or otherwise at the end of the talk. All right? Okay, the stage is yours.
Okay, thanks. Hi, I'm Thijs. I am a data engineer at DataWorks. I also own 2 dogs. I used to list other hobbies here, then we got our 2 dogs and they became our hobby. So I've been I've used quite a few programming languages over the years. My most recent addition to my arsenal has been Golang, and well, given that I'm talking about it, it's one I enjoy using very much. And my current client is the Port of Rotterdam, and we'll discuss a case from the port later in this talk.
All right, I'm Tim. I've done a PhD in chemistry, after which I moved into the data science. I've worked a few assignments, did quite some computer vision projects, and currently I'm at RHDHV and the Port of Rotterdam. And for me, you can talk about programming languages, but also GraphQL is something that I can talk in length about. But today we want to talk about machine learning in production, and how we can use other languages than the de facto language Python in there. But first, what's machine learning? Why do we do it? Well, it has now been believed, well, it's true, that from data we can get a lot of business value. And machine learning can add to that. So with machine learning we mean machine learning models, and a model is basically a mapping between an input and an output. An output we call predictions, and the input is our data. We train the machine to learn this mapping, so we don't have to program it explicitly ourselves. So machine learning can help us with automation of processes. One that's pretty big in the Port of Rotterdam, where we are, is asset management. But also trading can can be done with machine learning. But one thing that's really, really important, which we're not going in today, but if your data is not good, your model will also be not great. So garbage in, garbage out. So we are going to talk about machine learning in production. It's quite some work to get something in production if there's not already a platform there for you. So generally we start with finding data that can help us to get a model. We have to ingest it somehow, make sure that it's stored at the proper location, and then we can start exploring it. So exploration is generally done pretty dirty code, Jupyter notebooks, and then we can start cleaning it, and this is already, hopefully your code gets a bit better if you start cleaning your data. And at some point you can start training a model, and this can be quite heavy to do. That's why generally a lot of GPUs are also required. And once we've trained the model, we can serve it up, and other applications can start using the predictions of this model. One thing that is essential for having machine learning in production is that you monitor how your model is performing. So is it still giving different predictions is something you can check. Is it still confident about its predictions? And these are all things we can model. And once we see that these metrics go down, this can be a trigger to retrain the model with new data. So when we talk about ML in production, pipelines is one term that comes along a lot. Lots of this machine learning pipeline is basically software engineering. How do we get data from A to B? How do we transform it? And then there's this machine learning part to get a mapping from the input data to the output data. And then again, it's just software engineering. What send this prediction to the proper applications. So the functionalities of these pipelines, because this is quite a new field, have been crystallized over the past few years. Basically, big tech has all tried a lot of stuff, and now more or less the pipelines are becoming fixed, or at least the functionalities of these pipelines. So ML Ops is one thing that we always need to discuss, also, especially now. On the top, we can see that there's like the experimentation phase. We write some code, we write some packages, and at some point we have an automated pipeline to extract data, validate, prepare, train a model, evaluate the model, and validate the model. After which we go to a model serving phase. So this is our production phase. This whole pipeline can be considered as a machine learning pipeline, which is essential for having reproducible models working and also be able to quickly retrain a model. One thing to note is this metadata store below. Every component in these pipelines writes to this metadata store. So this is, I have been run with this type of data, and this is my output. And this is an important part. So one other view on machine learning pipelines to automate this is CD4ML, where there's a model building phase which can be triggered by general DevOps stuff. We still evaluate the model, productionize it, we test it, deploy it, everything. And what we see here below are all the artifacts that have to do with a machine learning pipeline. So it's not only code, as in general applications. We're also talking about models that has to be saved somewhere and save them correctly. So you can also roll back if your model turns out to be not performing. And this data, so this is actually the training data, but also the production data. If you can save it, due to GDPR restrictions, save it because it will help you debug your models or your whole pipeline actually. So what type of tools are there currently in the market to start building these pipelines? Well, one that's gaining traction is from TensorFlow, from Google, TFX. It has a lot of components, and all these components can be built into a pipeline. You can chain them, so we can generate train test data, we can get some statistics. This will help you also identify data drift. So if the reality around your model changes, your model might not perform as well. And looking at this statistics of the data can help you identify this. You can generate a schema, which helps you detect if the types of your data change. You can transform your data, which generally you have to do, scale it down or normalize it. And interestingly, this, if you have programmed this correctly, will be a computational graph, just like a TensorFlow model. Then we can train, tune, evaluate, and then finally push your model to production. Again, there's a metadata store to save all the metadata from each component, and this will also all interact with artifact stores. So, what is the main thing that we see here? It's that all these components are decoupled. And we can decouple them so that we have isolated functionalities, and we just write to metadata stores or data stores, artifact stores, how you want to call it. And in such a way, every component is a separate service, basically. So what we want to say is that because these are all separated, you don't have to use one package or one language for all components. So how do we go from an experiment, so I've looked at some data, I trained a model, to production? So what we think is go to production really fast, because that is the point that you can see actually how your model is behaving, how it's performing, how your pipeline works. And once again, use this metadata artifact store. One thing I needed to write down and tell from Thijs over here, he's going to explain it better, is that we should write applications and not scripts. This is an engineering view on looking at data science, and we as data scientists tend to write scripts. Alright, so once again, a large part of ML pipelines is regular software engineering. So, Go is an interesting language to do this software engineering. And herefore, Thijs is going to take over. and explain or present his experiences with using Go in an ML environment.
Right. So it's time to sing the praises of Go. Welcome to my church, everyone. As Tim mentioned, decoupling a data science pipeline, or well, just any application in general, but we're talking about data science products specifically, allows us to pick the tool for the job. So that means the right programming language, the right framework, the tool for the job. How do you transition from the transition from the experimental phase to production? What we encountered at Port of Rotterdam, and from what I've read and heard from others, it's quite a common occurrence, is that there are different standards and practices between data scientists and data engineers. This usually comes to fruition in the dreaded handover, which is the phase where a data scientist goes to an engineer, says, "Hi, I finished my code. Can you please put it into production?" So sure, but what do we mean with different standards and practices? As Tim said, I told him to mention, and I will mention again, is write applications, not scripts. So what we commonly see in data science code is that it's written as a script, so it's just a Python, and maybe it has a if name is main equals main, but it's really just top down, top to bottom. There's usually some functions. Sometimes there's also classes. But yeah, another thing is descriptive variable names. So that means, say I have a variable or a bunch of variables. They're named X, Y, Z, A, and AB. As an engineer, I have no clue what this variable is supposed to contain, which puts quite a bit of cognitive load on improving that code. Also, as software engineers, we like a clearly defined object model and clearer function signatures, and unit and integration testing of those functions and applications. To dive right into it, I'm looking at the screen on my left, but it's the camera's here. Here's a concrete example of a handover we had at the Port of Rotterdam. Let's first start with types and function signatures. So I have two functions here, or a function here. It's a get closest point, and it has a parameter called lines. That's all I know. I don't know what this is supposed to return. I don't know what lines is supposed to be. So that means I have to go into the rest of the application code and figure out what's supposed to go in here and what will I get in return. Another example, there's a class Centroid tracker. Okay, that's cool. That's classes. It has a method register, and it takes a parameter Centroid. Which again, what is a Centroid? So variables. The stuff on the right, it's pretty understandable. So we're doing some calculations, and that's all cool. But then there are, let's see, 4 variables. They're named U, D, G, and G. U, D, and G. It's 3. Sorry. I don't know what this means. Bit of a jump. Let's talk about Go. I told you I was going to sing the praises, and I am. What I really like about Go, and that's the first thing I tell people, is that it's a very simple language. It's easy to learn, and it has been kept simple on purpose. So one awesome meme about Go is that it still does not have generics after 10 years, which is true. But there's this very good reason, and I used to make fun of it too. But then I started using Go, and I started appreciating the reason why it doesn't have generics and certain language features that you'd expect in other languages. It's because the language has been kept simple by design. And that means unless we really fully agree this is an idiomatic way to do something in Go, we won't add it to the language. In and I won't bang on Python too much, but in stark contrast to Python, where it's, type-ins, sure, we'll add that. Walrus operators, sure, we'll add that. Match statements, yeah, great. So on and so forth. Which really leads to, and it's not just Python, it's most languages really, and that leads to quite a large variety of ways to write something in a language. Which means if you inherit someone else's code, the chances are virtually zero that you'll write that you'd have written it the same way. Whereas in Go, there's usually just fewer ways to write it, which means the Go code tends to be really consistent.
Does it have annotations?
Not annotations per se. It does have struct tags, which are some tags you use in struct fields, which can help with stuff like serialization. So it has sort of. It's statically typed, which is really important. So the Python code I showed you earlier, that just would not work in Go, because you'd have to define what type is this parameter, and what does it return. It's compiled, so it compiles to a native binary. So there's no, you don't need to have a specific Python version or a Java runtime. If you compile it, it'll run. And also because it compiles to a native binary, it's quite performant. Very important. It's just a nice language to work with. I just really enjoy writing Go code, which is an important factor in my opinion. And as people like to call Python the lingua franca for data science, I've taken the liberty of dubbing it the lingua franca for the cloud native ecosystem. I'm not saying that someone else hasn't said it before me. I won't go that far. I mean, the language has been around for quite a few years, and I have not written it during all of those. Also, another thing, if you've ever had issues with dependency management in languages, so think the Node.js, npm, left pad, fun stuff, and dependency conflicts, or issues with Python versions and conflicting Python libraries, and system versus virtual environments, and all that good stuff. It's not really a thing in Go. It used to be, from what I've been told, but as I've only recently picked up the language, I wasn't here to enjoy it. And the abstraction level in Go is another thing. So it's quite a low-level language in some ways. It doesn't have a lot of stuff built in some areas. So it does encourage and require an understanding of data structures and algorithms. But it's not like you're writing assembly or C++ or C, where it's so low level that you're really constantly reinventing the wheel. And there's a lot of awesome stuff built in as well that's really easy. So serving an API in Go is 3 lines and you're done. So the abstraction level is not that low that you can't be productive in it. Quite the opposite, in fact. Yeah, so how can Go help with the issues we discussed earlier? Language, because it encourages thoughtful code. It requires you to explicitly handle your errors. You can discard them, but your code will start doing really weird things if you do it. So you quickly learn not to. Because it's a simple language, it means you're writing simpler code, which means your code might be a bit longer, but it's also a lot easier to understand. Even if you've only been writing Go for a month. You can read most code bases. So I remember like 2-3 weeks after I started writing Go, I was able to just browse the Kubernetes code base and just really understand what was going on. That's not something I can do in, say, the Spark code base with Scala. That requires quite a few more years. As we mentioned with decoupled pipelines, given that a large part of machine learning pipelines is software engineering, my take is that all engineering, non-machine learning components can be written in any language, and because Go is awesome, why not use Go? And the performance here, I'll elaborate a bit on that. So Python, as we all know, isn't that fast. unless you use stuff with C bindings, so NumPy, data frames, all that. But then you're not really writing native Python, and also, well, you're writing Python, but you can't really use classes or objects. As soon as you want to write regular software engineering Python, you usually can't use those optimized performance tricks. So one important part of Python for data science and why it's so popular is the ecosystem. So because it's the data science language, there's also a large ecosystem that has built up over the years. So that's NumPy, Pandas, basically all machine learning libraries, plotting libraries. You have what have you, Jupyter notebooks also. So I thought it'd be interesting to see how Go does in these areas. And this is not to say that you should use Go in all these areas, absolutely not. It's just I thought it would be interesting to check it out. So I've classified it into 4 categories. That's data frames, which really is a category of its own because there's multiple solutions in Go and there's no one true Pandas. Numerical and scientific calculations, so that's NumPy and Go and OpenCV. Machine learning, so that's all your model training libraries, and data exploration. So I was expecting a different title here, but let's start with data frames. So this slide isn't quite right, but that's cool. Yeah, so there's a few data frame libraries in Go. The largest are, the most popular one is Argoda and QFrame. And there's also data frame Go, but all these are not as mature as Pandas. So they're all missing some features here and there. The interoperability between them isn't always that great. Let me quickly skip ahead. Yeah, okay, so OpenCV was supposed to be on the next slide. It's obviously not a data frame library. Yeah, so as for numerical and scientific calculations, the most important one here is GoNum, which is a really quite extensive and very mature set of numerical packages. So that's yeah, just your matrix calculations. There's all sorts of mathematical packages in it. There's also a plotting package in it. OpenCV was supposed to be on this slide, so we're at the port. We're doing a computer vision project, so we're using OpenCV quite a bit. So I experimented a bit with the GoCV, with the Go bindings for OpenCV, and that really works well. It's very mature. There's also sklearn, which I didn't want to mention here, but yeah, as I already put in the slide, it's a inactive project. So this list could be quite a bit longer if I included projects with commits from 2019. But one thing that I feel is important, that if you're picking a library to depend on, that it's actively maintained. So that thinned out the list quite a bit. But it looked quite okay, so I did want to mention it. And then there's machine learning. Also not a very mature part of the Go data science ecosystem, although Gorgonia is looking quite good. As it's not my area of expertise, I can't really tell you much more about it. There's also GoLearn. These slides will be available online, so to say you're having a boring evening, you'll be able to click the links and check them out for yourself. And lastly, because we all love our notebooks, there's also a Go kernel for Jupyter notebooks. Though I wouldn't necessarily recommend using Go for data exploration. I think Pandas is much more mature. Again, I did want to mention it. And there's also a plotting library in GoNum. So, as for our case at the port, as Tim mentioned, asset management is quite an important area for us. So one thing, the project we're currently working on is a machine learning inspector, which means there we have these inspectors driving around in the port, and they used to get out of the car and manually inspect all sorts of assets, so that's traffic signs, the condition of the road, etc. And we're trying to make their life easier by just having them drive around with a camera on their car and automating their work so they can really focus on the more important parts. And so this means we have a camera mounted on a car. It's driving around. We're tracking the GPS location, which means we get a whole bunch of images, and then we run a model to detect certain assets. And then if we just stop there, we have 100 different assets, because there's 100 separate frames. We've detected a road sign 100 times, so that means there's 100 road signs, right? No, obviously not. So the next step is that we start tracking these objects. So we look at each frame, and then we look at, hey, can we determine whether this is the same object or not? So then we just have two, lampposts here, road signs, whatever, instead of 100. And then we also want to localize it, so we want to know where is this traffic sign. And that's a bit of the code I'll show you now. Right, so one of our data scientists had written some code to do this tracking and localization, and then there was our beloved handover. So this is what the code looked like, sort of. So we had an agreement beforehand. They'd write the core logic of the application, and we'd write we should make sure the data got in there, and it all fit into the application. So she stubbed out some functions. And so I took a look at it, and it said, okay, each detection should contain a detection ID, a bounding box, a class ID, and a centroid. And it should return a list with dicts. Yay. So how was this used? This was used like this. So this is the detections. The method I just showed you. Then there's we're making a dictionary here. We're making some more dictionaries elsewhere, I believe. Also there's NumPy arrays. This is all, as an engineer, I don't really immediately get a feel for how the data flows through this application, what's returned, what the output is. It was quite difficult to fathom. Dicts everywhere. So, and this is one of the, this is part of the localization code. So if we're driving, we took a picture of a lamppost there. We're drawing an array from ourselves to where the detected object is. And again, this is what the code looked like. So there's some parameters here. This is all quite doable. There were some more doc strings, but it would be quite a lengthy, long slide. And we're returning some NumPy array again, and we're returning a data frame, as you should. So the output of the previous of this function is used here. Here it's called lines, not rays. And again, we have that's where the fourth variable was. I mentioned the three variables with awesome names earlier. Here's the fourth one, M. So I asked our data scientist where did these variable names come from. She sent me the paper that she used to write this code, and then I understood. So that's what they are called in the paper. So I'm not blaming her. It was also quite a tough paper to digest. But yeah, take a moment to let it sink in. If you don't really understand what's going on, that's cool. I didn't either. So I went back a bit, and I proposed to our team, hey, so I'm going to have to do quite a bit of refactoring here, and I'd also like to do an experiment. I'd like to see if I can write this in Go. not just because I like the language, but also because I think it can help us in the future with future components. And I'd like to see, because it's a simple language, and it's quite descriptive, can we use this in future similar types of components? So I started with defining an object model. So earlier I said something about detections, and it has a such and such. So we're beginning with a video. A video has it was made with a camera. It contains certain information we need. It has a bunch of frames. We also made a bunch of GPS measurements. And this video had a certain resolution, so a height and a width. And all these have nice data types, so I know what it's supposed to be. Then the frame has location information. It obviously belongs to a video, and we made a bunch of detections on this frame. And then the detection has a confidence score, a bounding box, so that's the box around what we detected. Also a segmentation. That's how do you describe it? Exactly where we detected things instead of a rough box, the exact outline. We calculate the surface, which is relevant for some objects, for some assets. And we're detecting different kinds of assets, lampposts, stuff on the road, etc. And then it's part of a tracked object. So a tracked object, is what I showed you earlier. Instead of 100 road signs, we now just have 2. And this road sign was detected in these detections. And then we also define a bit of behavior for these types. So there's a pixel angle ratio, which is something. Oh right, this is the angle of view of the camera divided by the width, etc. It's not really relevant what's in these, it's just that this is a behavior of this type. Yeah, so the centroid function earlier, that's a method of a bounding box. So that's just where's the center of the bounding box. And this is what the ray function looks like now. So we still have the function name, but now we're returning a model. We're putting in a detection. We're getting a ray back. I didn't show you the ray struct, but trust me, it's a thing. So here we it's the same code really. Yeah, but I thought it was just a bit more readable. This is the fun one. So this is where the most math was involved. This is the one with the brief the variable names, and as you can see, I also didn't know what else to call the variable but G. Again, that's in the paper. Yeah, it's G it is. It's can't have it all. And what you're seeing here, this is all the GoNum library. So this is where we used NumPy earlier and data frames. Here we're using the Go library. So we're making a dense vector. We're doing some operations on it. And then it's been a while since I wrote this code, so I won't be able to exactly talk you through it. If you're comfortable with scientific and numerical code, hopefully you understand a bit of what's going on. Point being, my output was exactly the same as the code we got originally. It's just a lot more maintainable, and it really integrates much more nicely into our application. And our data scientists, I checked, they could also follow what was going on, so that was nice. So yeah, it's just an example of what a bit of Python rewritten to Go looks like. It's not all run sunshine and rainbows though. Sometimes you really do have to reinvent the wheel where you don't want to. So NumPy has a nice method to go from a Euler rotation to a rotation matrix. GoNum doesn't. it was mentioned in the comments in the GoNam code, and then they had a whole discussion in the GitHub issues about why Euler rotations are horrible, and that's where they left it. So I had to write this one myself. It's yeah. Don't look at it; it's hideous. But so it's yeah, there are some rough edges here and there. But again, you have to write this once, and then you have this function. So conclusion. Go lends itself well to numeric and scientific calculations. The GoNam library, though it does have its quirks in the way you write your, you have to write things. It's really nice to use. There's also great documentation around it. Community is really nice, and it's actively maintained. Very important. Python still works well for experimentation and exploration. So it's not, I'm not proposing you drop Python immediately, never touch it again. Absolutely not. It's just for where engineering is involved and where you're really going to production, I just want to suggest you also consider using other languages because it's really nice. Yeah, and it's not just some experiment that you can do in your attic, but never really when you're being paid for it. This is something I can actually recommend you use in the real world. And I think that's it.
There was a question from the audience. When data scientists use Python, sometimes they have to switch to C++, something at very low level because calculations simply take too long. So they have some hybrid constructs in order to let the code execute fast. Is there something like that possible? Calling Go for certain subroutines that have to be fast from Python or some?
I think you can. I don't think you should.
Why?
Because if you're writing that part in Go, why not write the other stuff in Go as well? So for C++, I've read quite a bit of C++ the last few days, and I really wouldn't recommend using it because, I don't know, it's complicated, it's convoluted, and it's complex, and it really distracts from the core logic you're trying to write. That's not the case for Go. You can really write small, succinct applications. So I would just recommend writing it in Go in that situation.
Yeah.
Because the reason you're using Python and C++ combined is because you want the performance of C++, exactly. But you don't want to write C++, which I understand. So write Go.
How fast would you think someone with Python experience can get started in Go, and what would be the most difficult change of thinking when writing Go? Maybe Tim has some experience as a data scientist.
Yeah, I started Python in 2008 and Go maybe a year ago on a hobby basis. And reading, for example, his code for me is now quite easy. The big struggles are the typing. There's an interface which feels a bit counterintuitive for a Python developer.
That's not just for Python developers. Go interfaces do take a
Another mindset.
Yeah, another mindset. They're implicit versus explicit, and that it's really weird in the beginning.
But I have to admit,
Pointers, maybe?
pointers are a bit weird, and not having a package for everything is something to get used to, but it's also, for me, a fun challenge, personally.
The copying by reference, copy by reference and passing by reference.
That's something to get used to, copying and passing, yeah.
Yeah, but that's, I think, the main struggle you get when writing.
Yeah, true.
Yeah, especially if you're not so in Python, you're not really aware of this, and yeah.
Now, one last question: how well does it actually integrate with Infinidash?
Amazing.
Okay, so it's really top of the art.
Yeah, but that's really more due to how awesome Infinidash is, obviously.
Okay, you've been falling in love with Go. I can see that.
We're getting married soon.
Perfect. All right, I think we conclude the meetup. Thanks, guys. Yeah, these guys have been falling in love with Go. I can see that. So please If you also want to fall in love, contact us and we'll help you with that. We have the means.
Yeah.
Thanks everyone for being here. Thank you guys for holding this talk. I'm very curious where the Port of Rotterdam will go. With go, has to be a pun in it, right?
Sure, of course.
And see you in about 2 months, and I hope that we'll have then the party here in our office with a proper meetup and pizza and ties. Again, we'll let you know as soon as possible.